Hello, this will be a demonstration of proposition 15 from book 6 of Euclid's Elements, which says that in equal triangles which have one angle equal to one angle, the sides about the equal angles are reciprocally proportional, and the partial converse, triangles which have one angle equal to one angle and the sides about the equal angles reciprocally proportional are equal to one another. What we're given is two triangles A, B, C. And A, D, E, having the angles at A, namely BAC and DAE equal to each other. And we're going to place the two straight lines, CA and AD, in a straight line with one another, from which it shall follow that BA and AE will also be in a straight line. The argument is much the same as in the previous proposition, so I won't recount it here. Point is that CA and AD are in a straight line, and BA and AE are in a straight line. And it is either going to be the case that the triangle ABC is equal to the triangle ADE, or that EA is to AB just as CA is to AD. If the triangle ABC be equal to the triangle ADE, then we shall prove that CA is to AD just as EA is to AB. Or, on the other hand, if we are given that EA is to AB just as CA is to AD, we shall prove that the triangle ABC is equal to the triangle ADE. Now let's deal with the first case where the triangle ABC is known to be equal to the triangle ADE. We'll begin by joining the straight line BD by postulate 1. Now, knowing that the triangle ABC is equal to the triangle ADE, we were given this information. And knowing that equal magnitudes have to the same magnitude, the same ratio, that's proposition 5-7, we can say that the triangle ABC is to the triangle BAD, just as the triangle ADE is also to the triangle BAD. But we notice that the two triangles ABC and BAD are under the same height, which means by proposition 6-1, they are to each other as their bases. So the triangle ABC will be to the triangle BAD, just as CA is to AD. And likewise, we shall notice that the triangle ADE and the triangle ABD are under the same height, which means, again, by 6-1, they are to each other as their bases. So the triangle ADE is to the triangle BAD, just as EA is to AB, which means by 5-11, we have ratios which are the same with the same ratio, which means they are the same with one another. So we can say that CA is to AD, just as EB is to AB. And this is what we wanted to prove. Given that the angle ABC is equal to the angle DAE, and that the triangle ABC is equal to the triangle ADE, we had set out to prove that CA is to AD just as EA is to AB, and we have thus proven it. So we are done with this first case. Now the second case, having been given that EA is to AB just as CA is to AD, we're going to begin again in the same way by joining the straight line BD by postulate 1. Now, having been given that CA is to AD just as EA is to AB, and again, noticing that the two triangles ABC and ABD are under the same height, which means that CA is to AD, just as the triangle ABC is to the triangle BAD. And so too, EA is to AB, just as the triangle ADE is to the triangle BAD. Again, because the two triangles DAE and DAB are under the same height, which means they are to each other as their bases. That's proposition 6-1. Which again means that we have multiple ratios which are the same with the same ratio. So by 5-11, they are the same with one another. So the triangle ABC is to the triangle BAD, just as the triangle ADE is also to the triangle BAD. But magnitudes which have the same ratio to the same magnitude are equal to each other by proposition 5-9. And so the triangle ABC being to the triangle BAD, just as the triangle ADE is to the triangle BAD, the triangle ABC is equal to the triangle ADE. And this is what we set out to prove, which means we are done with the proposition entirely. Therefore, etc. QED. Got nothing to say about this proposition, nothing to add that is not manifest. So I will end the video here and move on to 6.16.